All right, so we're now recording for those people who are out today. All right, we're on Module 3. It's Labs 5 and 6. Y'all have a page number?
21.
21? Page 21. All right, we're going to be looking at some kind of crazy stuff today, some introductory stuff for chemistry, but yet it's going to be profound and necessary to be needed the rest of the year, okay? So we're going to start off with some really smart guys who figured stuff out and went before us, sort of like with our periodic chart of the elements, right? People went before us and they figured some things out. They're real smart. Do y'all have your periodic charts with you today? We're going to probably need those during the lecture time. So this is William Crookes. He's a British chemist, and he started wondering about electricity going through different elements. All right, so he wondered if he could send electricity through them. So he had that question, can I send electricity through them? Then he had an hypothesis, which is I think I can send electricity through different elements. And then he devised an experiment to do that. And what he came up with was this thing right here. So that's called Crookes tube. And it's just like a light bulb with a filament down here. And what he would do is he could fill this right through here. He could shut this off like a vacuum right here, but he could fill it with a certain gas. So he tried different gases of elements, and then he shined electricity through them. And when he shined the electricity into the vacuum tube, he noticed a glow. All right, so there was a glow at the end of the tube over here. And so then he started to wonder, okay, well, there I can shine the electricity through there and I can have something happen. Now the question is the thing that's coming out, is the electricity that's coming out, is it in particles? Am I shooting particles through the tube and that is causing that to start glowing on there? And he actually called the particles a cathode ray. So this is also known as a cathode ray tube, and it has to do with the end, the charge on there, positive, negative charge. So it was the positive charge was the cation, the cathode ray. That's how he came up with the name for that. And he came up with another idea. He said, well, in order to answer my question, are they particles, what can I do to my experiment? He said, I know, I can put up a little barrier. So he put up this little barrier right here. It's like the shape of a cross. And he thought if those cathode rays were hitting there, if they were particles, then they would be blocked by that little cross. So he did his experiment, and check it out. You see right here, you see the shadow of the cross on the end of that tube. So then he was able to draw a conclusion. I'm shooting out these rays. Those rays must be particles, and those particles are being deflected by this, and I'm still glowing on the end of this deal. All right, so his tube looked like that. His cathode and his anode, and there it is right there, the shadow of the metal cross. All right, so he did that. He said, okay, so his conclusion was we have these little particles that are coming out. So another guy comes along, J.J. Thomson, and he says, I think those particles are actually part of the gas. I think those are part of the atoms of the gas, and the electricity's going through them. So he did experiments with magnetic and electrical fields, but he actually reasoned that the charges in Crookes' tube were coming from the gases, and that those ingredients were part of all atoms. So he actually tried different gases in there. So he put, neon gas and argon gas and all these different gases, helium. And interestingly, another side note, which we'll get to toward the end of the lecture here, is that in every different element that he put in there, there was a different color of light at the end of the tube. All right, so obviously with the one that Crookes did, it was a green, but there were all these different colors. And he's going to make he's going to draw some conclusions there. Now, he modified the tube a little bit because he said those things, if they're coming from the atoms, I believe because we have electricity that has charges to it, I think they're charged particles. So not only are they particles coming from the gases, they're charged particles. So how can he test that? He takes the same kind of cathode ray tube with the electricity coming in through right here, and he put next to it a magnet. All right, so now these rays are going through this magnetic field, and the magnetic field deflected those particles up to one part of the tube there. And he said, okay, well, they're deflecting it like this. And he said, what's being deflected up here, see that positive metal plate there? So the negative charges, there are negatively charged things that are being deflected up onto the light bulb that way, up onto the tube that way. And so he said it's electricity, and he named it. He named it a negatively charged particle, and he came up with the word electron. All right, so because electricity with the negative particles coming in through there, so it was J.J. Thomson who came up with the word electron. All right, he also noticed that there was a ratio of the charge to the mass. Whatever mass he put in there, the way that when he signed it through there, he could get a ratio of the charge and the mass of the negatively charged particles, and it was always the same for each element. So then he started to reason, okay, well, the element that I put in there had no charge. It was neutral, all right? So it was neutral to start. There must have been an equal amount of positive charges in there as well, and it actually works for every element. So he said he wrote that down and said it's interesting. He had a student, he came up with this idea. He said, okay, I think we have positive charges and we have negative charges, and they're suspended inside this thing we call an atom. Now this is a British delicacy, I guess, called plum pudding. I had to look it up. I was thinking pudding with, we talk about pudding being kind of a liquidy thing. But this is a plum pudding cake, and so he named his model of what he thought the atom looked like off of plum pudding. And so it looks like that. He believed there was like a positive charge of this sort of pudding stuff, and these negatively charged electrons that he named were suspended in there just like plum pudding. And it was his student that came by and said, well, that's interesting. And this is Ernest Rutherford. He was a student. He said, if there is a negative charge called an electron, there's obviously something that's a positive charge. He agreed with his teacher, and he called those protons. So Rutherford is the one who gave the name protons to the positively charged things. And he tested the plum pudding idea, and he actually disproved it. And he suggested a new model, which we're going to call the planetary model, also known as the Rutherford model. All right, because what he did was a very famous experiment. But first of all, the way he did it was this. This is an alpha particle. It happens to be something that had been discovered about the time. There are some elements out there that naturally fall apart. It's called radioactive elements. And they naturally fall apart. And one of the ways they fall apart is by this process called alpha decay. If y'all remember from physical science way back, do you remember this? Alpha decay. They send out what's known as an alpha particle. And if you look at the alpha particle, it's got 2 protons and 2 neutrons. 2 protons and 2 neutrons. That is a nucleus of a helium atom, because 2 protons, right? There's no electrons on it. So it's not the actual atom, but it's the nucleus of the helium. So there's this nucleus of the helium atom, and it's being shot out of these radioactive particles at a high speed, like a bullet. And so what he did, he said, okay, well, I had this positively charged alpha particle. I'm gonna test the plum pudding model to see if I can send these positively charged particles through different elements and see what happens, see what kind of deflection I might get there. And so he had the famous gold foil experiment. So there he had this screen around here. It's a detecting screen that had zinc in it, and when the alpha particle hits a zinc screen, it glows. It hits it and there's like a little glow on there. And so he said, I'm going to send the alpha particle through this gold foil and see if, according to my teacher's model, Thomson's model, if all of the rays go straight through right here. So his theory was this: if the Thomson model is correct, there will be the positive and negative evenly distributed into the pudding area, and they'll just travel straight through. Maybe a little bit of motion. I'll show you in a second that one. But something else happened. This did not take place the way he expected. Let's see what happened.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, so what happened? So if Thomson's model were correct, then there would be some sort of movement. So remember, the particle going through is positively charged. So therefore, when it gets attracted to the negative charge, but it gets repelled by the positive charges. But overall, it should pass straight through. But that's not what he got. What he got was something like this, where he had deflections, so this positive was being deflected away and sometimes even bouncing straight back. Now, the vast majority of them went straight through to the screen, so there was a brighter spot on the very part of the screen that he anticipated there being that. And he noticed that mostly what's going on is they go through because atoms are mostly empty space. It's kind of like between us and the moon, there's empty space, right? So we started to postulate and that's where the planetary model came out, that there was empty space in between there, and that the positive charges must be concentrated in the middle. And he called that middle the nucleus. All right, so then he comes up, he says, okay, I think it's like this. We have a massive nucleus, it's big, it's positively charged, and it's in the middle, and then we have empty space, and then we have these little electrons that are spinning around, or the electrons are out there. He didn't know they were spinning necessarily at this point in time. So then we're going to see we have our three things, our electron, our proton. The neutron was discovered much later. It has no charge, but it has mass, and they found that out by measuring masses. Here's Rutherford's quote: "Of all created comforts, God is the lender, you are the borrower, not the owner." He was a great man of God. Every time he discovered these new things about chemistry, it made him his faith deeper in God. So that's pretty cool. Okay, so two principles, you're going to write this down. And these are with electricity at this point. This really could be part of physics. Like charges repel each other. You know this with magnets too, right? The two north poles will repel each other. Opposite charges attract each other. And because of that, they were able to do these experiments to check out what was happening inside that atom. Remember, atoms are too small for us to see, and we'll never see them this side of heaven. They're just too small. I think there's a really strong microscope in heaven that we can take a look, and we're probably wrong. We'll find out. We'll go, oh, that's how it works. Okay. All right, we got that. So here we go. Every substance has an electrical charge. Y'all may have noticed this when we have static electricity in our hair, this kind of thing. Most of the time, we are looking at neutral things because there's as many positive charges as negative, therefore no overall charge, and the substance won't have electrical charge. But if there's an imbalance, which is what happens with our static electricity, electrons carry on stuff, we will get a negative charge. So we have attraction between negative and positive, and repulsion between like charges. Okay, so what is the structure of this? We know that now that there are three components: protons, electrons, and neutrons. Protons are positively charged, electrons are negatively charged, and neutrons have no charge, but they have mass. The atomic number on your periodic chart of the elements tells you how many protons an element has. But since they are neutral in charge, then we can assume, therefore, that they have the same number of electrons as well. Although, as I've mentioned before, when the electrons get moved around and shared and given away, that's chemistry. So that's what's going to happen when you start mixing things together. But in general, we're going to assume that every element in its ground state is going to be neutral. It's going to have the same number of electrons as protons. But officially, if I ask you, what does the atomic number tell us? You're going to say number of protons. That's the official answer, okay? Now, what is an isotope? It turns out that there is, sometimes there are more neutrons. Neutrons can be changed inside of certain atoms. So the mass number tells you the total number of protons. So this is a mass number. That's at the bottom of your little chart there. An isotope is an atom with the same number of protons, but different number of neutrons. So the only thing that changes for that atom is its mass. It gets heavier. It gets more massive. Isotopes behave identically to each other as far as chemistry goes. The main difference between them is their mass. And then the mass number tells you number of protons plus the number of neutrons. So we can do a little math there and figure out how many neutrons anything on the chart might have by just subtracting from the main number how many protons there are. I'll have that little formula for you that fits in your book in the right place here in a few minutes. Y'all had to write all these words? Bummer. Just like college. Okay, so for instance, these are 3 isotopes of hydrogen. Most hydrogen, which we call protium, has 1 proton and 1 electron, and that's it. Right now we're just looking at the nucleus. The vast majority, I wish I had percentages on here, I think something like 95% of all the hydrogens out there have just 1 proton, no neutrons at all. But every now and then there'll be one with 1 neutron. We call that deuterium. And then one with 2 neutrons, heavy hydrogen, which we call tritium. Okay, so those are all isotopes. Now you might say, well, this is hydrogen and this is an isotope of hydrogen, this is another. No, they're all isotopes. It's just the most common one is 1 proton. Okay, so this is when you might need your chart. What is the name and the symbol of an atom that is made up of 10 protons, 10 electrons, and 11 neutrons? Who's got it? 10 protons, 10 electrons, and 11 neutrons. It's an easy question.
Is it neon?
It's neon. All right, but I want you to look at it real quick. Why do we know it's neon? Because how many, what's its atomic number? 10. 10 means it has 10 protons. Okay, that's all we need. Now look at the mass number beneath it. At the very bottom, does the mass say 21? 20.8.818? All right, so every now and then it's going to have that extra one in there. Okay, that extra one in there. So this one had 11, so that meant instead of neon with a 20 up there, it was neon with a 21. It was an isotope, right? How many protons, electrons, and neutrons make up a I-129? So look up I, which is iodine, and it's got 129 things in the middle. It's got adding up protons and neutrons to 129. So you can tell me already how many protons are in there. Say it again. 53. So what's 129 minus 53? I think the math is on here. Here we go. 53 protons, 53 electrons, right? And 76 neutrons. So apparently 76 plus 53 equals that number. Y'all tell me whatever it was. 129. Okay, do you get it? Okay, so that mass number down there will give us the number of neutrons. But remember, the protons will never change. If the protons change, it's a new element. It's a different element. That only happens in in radioactivity. Okay. All right. What about nuclear fuel and nuclear bombs? How does that work? Well, there's a number 92 on the chart. It's called uranium. Uranium is naturally part of it. One of them here. U-235 is unstable. All right, so it has, so the U-238 has 146 neutrons. The U-235 has 143 neutrons, and it's unstable at that. It's out of balance. And because of that, it'll fall apart all by itself, sending out some particles, either alpha particle, beta particle, which I can't remember what uranium does at this minute. And then part of it, some of them have only 142 neutrons. But see, they're very heavy. They only have 92 protons. And so what we can do is we can take this right here, U-235. It's only 0.7% of naturally found uranium in the earth. We mine for it. And the way to do it is to enrich it by basically getting everything else out and ending up only with this. And the way that you get that is a secret. It's a top secret, because if you have that, then you can make a bomb, a nuclear bomb. And we want to avoid that. Yeah. All right, here comes our nuclear bomb. Boom, right there. And nuclear bombs are very damaging, so I want to stay away from those. All right. Rutherford's experiment showed that the atomic theory was consistent with the data that he was getting. Okay, so his planetary model, that's not too bad for 1910. And it was only after that that they found the neutrons. Oh, you need that?
Yeah.
Consistent with the data. And that was that there was a proton, the protons were concentrated in the middle, the electrons were outside, and mostly there was empty space. And if any of you want this recording, you can get to that now. It'll be one of those YouTube things, right? Are we good? All right, and then we just show here, just real quickly, how to get the number of neutrons is to take the mass and subtract the atomic number, which are the number of protons. Okay, we already did that a little bit, right? But that's the formula for it. So if I ask you to find neutrons, you're going to need two things. You're going to need the atomic number, which is the number of protons, and you're going to need the mass number. So the thing you're going to need most of all is your periodic chart of the elements, which next week for your quiz, be sure to bring that, okay? All right, what about the light? Okay, so remember it was producing light at the end of that? So some people started wondering, well, what about the light? What's the deal with that? Rutherford's model wasn't consistent with the way the light was behaving. Because what happened was it was glowing up against the end of the tube. It was glowing on that zinc screen right there. And they thought, well, what in the world is happening? If they're glowing all the time, that means energy's being released, and therefore the revolution of the electrons going around like he claims to be the model would always be glowing and therefore always be slowing down, and they were destined to crash into the nucleus. They were going to just like a toilet flush, and they're going to go right down into the middle like that. But just looking at those parts of light, that's what happens to with the function of light. And so that's when we have to, now we're going to discuss light a little bit. What is the nature of light that we know? And they knew this then too. There were physicists and chemists working together. Light has no mass and takes up no space. That's what we believe at this point in time. We have not disproven this yet. Light is not considered matter. It's actually considered radiant energy. So radiant energy. And some people would call it pure energy. And then we're going to look at this right here. It's something called the dual nature, the duality nature. And that is that sometimes it acts like a wave, and sometimes it acts like a particle. So when Crookes shined it through there, you know, we have these little electrons that are coming off like that, and that light on the end might be particles over there, or they might have been waves coming in right there. So this is how we do the wave particle, the dual nature. Sometimes it behaves like a wave, sometimes like a particle, and so the whole wave particle is a possibility. In other words, it's both at the same time. In a weird way, we haven't understood this completely yet. Okay, we're still working on this. But those are our little packets right there, and those little packets of wave energy particles are called photons. This is somebody's idea of the wave in the particle known as a photon. All right, and so those are like little BBs coming out every time the light turns on. And then sometimes it's wave-like, sometimes it's particle-like, and this is the wave-particle continuum right there, sort of the whole Albert Einstein idea. All right, you're going to need to draw this in a box somewhere on your book. You're going to draw a wave going up and down and up and down, and that line in the middle right there. And you're going to label a few things. So they're just like waves of the ocean. At the top of the wave, that's known as the crest. And at the bottom of the wave, that's known as the trough. And then I need you to see here from the middle of the line to the top. You could also go middle line to the bottom of the trough. Those are equal, by the way. That's known as the amplitude. Sometimes you'll see pictures that takes the amplitude all the way down. That is incorrect. The amplitude is from that midline to the top. That is known as amplitude. And then from crest to crest or trough to trough, that's called the wavelength. And those are the same. Crest to crest, trough to trough, same thing, the wavelength. And it turns out that the amplitude is going to tell us how bright something is, a bright light. The higher the amplitude, the brighter the light. The wavelength from here to here is going to tell us what color the light is. So now we're going to start to see those different colors of the gases. It's because they were producing, guess what? A different wavelength. And then frequency is how many times it hits me. Okay, if you think if you're standing at the beach and a wave hits you, and if you counted in between each time the wave hits you, that would be the frequency of the waves. The waves can be really, really close together with a high frequency, and those are high energy waves, or really stretched out low frequency, which are low energy waves. And we'll see that on the whole electromagnetic spectrum here in just a minute. It also has magnetism associated with it. This was a big breakthrough. This was the physicist who figured this out. It was Michael Faraday. If you remember from physical science, we talked about Michael Faraday, where we have the electrical field going up and down. Here it is, boom, boom, boom. And kind of perpendicular to it wow, we have the magnetic field going alongside. So electricity produces magnetism, magnetism produces electricity. That's very helpful for us. We use it every day to power your houses. Okay, that's how you're getting power to the lights in your house, through magnets that are moving at a dam somewhere. All right, here is our spectrum. You're going to write down Roy G. Biv in those boxes. Red, orange, yellow, green, blue, indigo, violet. Notice it's backward here because I guess we couldn't spell his name, Vib G. Yor. So we put it the other way just for that word. But the higher frequency is up here, the higher, and down here the lower. All right. So Roy G. Biv, and y'all all know what that means. You don't have to write the word red, orange, yellow, green, blue, indigo, violet unless you want to. But those wavelengths show those different things. So what color wave has the longest wavelength? Check a look. These numbers will tell you. It's this one, yeah? So red. And which color has the shortest on the other end? Violet. You could say purple if you want. So we know, of course, this makes our rainbow, yes? There's our rainbow. And we can see that the light is being bent at a certain angle, and then it's being then brought out here to that wavelength out here to these different colors. And this, of course, is in the electromagnetic spectrum in a very slender area of the EM spectrum called visible light. And it's the only thing we can see. There are creatures out there that can see different parts of the spectrum. Some can see over here in the UV areas, ultraviolet. Some can see over here in the infrared. I think, is it bees or something that don't see any red at all, but they see over here in the UV. That's why, is it bees or birds? Bees don't pollinate red flowers because they can't see them. So that's why the hummingbirds like red. They can see them. The speed of light, do y'all have that in there, speed of light? 186,000 miles per second. It's very, very fast. It is a constant. The constant is called c. It is something we're going to use in math problems here in just a minute to look at the frequency of light, and because light is traveling at a certain fixed speed. It's called the speed of light. The number we're going to be using is the one here in the metric. Instead of miles per second, we're going to be using meters per second, and it's 3.0 times 10 to the 8 meters per second, and it's measured in 1 over second. That's its units of measurement. And 1 over second equals something called a hertz, named after Mr. Hertz, who had done work with light and the way it travels. So in a vacuum, it travels at 186,000 miles per second. I think it's rounded up in your book to 190 miles per second. It'll slow down a little bit in water to a very, very slow 140,000 miles per second, and through glass even slower, and then through diamond the slowest at 77,000 miles per second. And they've been doing some interesting work with this where they make diamond and things like that very, 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 very cold, like almost to absolute zero, and they've slowed it down where you can actually see it moving like that, which is pretty cool. So they've slowed it down that much. All right, this is a formula that if it's not written for you, you need to write it down. F for frequency equals c, which is the speed of light, 3.0 times 10 to the 8, divided by the wavelength, that is the letter lambda. The Greek letter lambda. And so we're going to use this for some math problems. They're not difficult math problems, but I would recommend bringing a calculator. I'd also recommend doing your practice problems in your book, okay? And because we're going to rearrange those a little bit, sometimes they'll give us the wavelength and not the frequency, that kind of thing. The dirty trick there, right? So let's try one. Here we go. A violet wave has a wavelength of 405 nanometers. What is its frequency? All right, so we're looking for F. That's nice. We know the frequency was given to us, 405 nanometers. And we also know C, which is the speed of light. But it looks like we're going to have to make a conversion here in order to get the units to match up. All right, so 1 nanometer equals 10 to the negative 9 meters. So that's our conversion relationship right there. So I take my number that I start with. Always start there, y'all. Take the number that was given, put it over 1 if you're doing a conversion. Put it over 1. So I take my 405 nanometers, I put it over 1. That's a really, really small measurement, right? So that's why we have to use it for light, because it's very, very small. And then I'm going to use my conversion relationship. I'm going to cancel out my nanometers. and I'm going to figure out what my meters are. So I have 4.05 times 10 to the negative 7 meters. Do your calculator let you do the negatives and all that? The negative? Oh, good. Oh, good. Because this is where I would totally miss a zero on this. I know I personally would. I'd have to put all the zeros in, 0.000, and then I'd have to do my zeros. Yeah, I'm going to lose it. So if your if your calculator does that, practice that a couple times on your practice problems using that function so you can use it in the quiz, okay? Okay, so now I have everything I need. I'm looking for frequency. I know what C is. That is 3 times 10 to the 8 meters per second. And then I can put it over the number I have here, my 4.05 times 10 to the negative 7 meters. And I'm going to come up with 7.4 times 10 to the 14, 1 over second, which do you remember what that's called? It's called hertz. So the answer would be 7.4 times 10 to the 14 hertz, which is 1 over second. So the math is not difficult, as long as you remembered I have to get my conversion right there. And I will tell you that those light frequencies, wavelengths, are always going to be in those nanometers. So, all right, that means that 7.4 times 10 to the 14 waves hit you each second. Waves of violet hit you each second. Like when I turn the light on, you're going to have some violet in there because all of them are going to be in there, and they're going to be hitting you that fast. So boom, boom, you're being bombarded by it. A light wave has a frequency of 4.70 times 10 to the 14 hertz. What is its wavelength and color? Interesting. So we know what C is. Okay, we know that if we want to do some conversions right here, right, our nanos right there. So we are looking for, we have the frequency, 4.70. So we're going to change our little thing around with a little algebra right there and find, we're looking for the wavelength. So it looks like we're good. Yeah, and everything right there. All our numbers are put in. Do you see how I got to here? We're using this formula right here. And those numbers we just plugged in. Our units are okay. So I get 6.4 times 10 to the negative 7 meters. All right, so that's my answer for the first part. What is its wavelength? My wavelength, lambda, is 6.4 times 10 to the negative meters. Negative 7 meters. So now to get the color, I need something more. I have to go to a chart that we have. To figure out the color, refer to the figure 3.20 on page 100 of your book. And that's when our conversions come in right here. And we find it 640 nanometers. We look on the little chart there to see what color is showing at 640 nanometers. It turns out it's orange. All right. I don't know if this second part would be on a quiz because I don't know if I'm going to be able to give that to you, that chart that has all of those, unless you memorize all those, which I don't ask you to do. All right. But it's an orange light right there. All right, which brings us to the electromagnetic spectrum. We've been talking about visible light, which is right in here. I'm going to have you write this down in those boxes. Don't write this just yet. I have an easier one for you right here. But I want you to see how the waves over here, they're really far apart. Then they get closer. So they get more and more. They're shorter wavelength, the more energy there is. And the more energy there is, the more damage that can do. But way over here on our low frequency waves, we have things like the radio. Y'all listen to the radio? You ever seen it, like you're tuning, you have to tune the radio in, right? You have to find the right frequency of that wave coming in. And sometimes it's kind of a crummy reception, and so that's because, in fact, if you think about it, y'all probably listen to FM radio, right? And all the FM radio mostly have pretty big numbers. I don't know if you pay attention to the numbers. The bigger numbers mean they're going to have a larger wavelength, so that they're going to be stronger. They're stronger waves. I listen to AM radio and it's like 590. It's way over here, and so I really have to move my radio around and that kind of thing like that. Here's the one I want you to draw because it's going to be easier to draw. You're going to start with we're going to see we're going the other direction. All right. So in your deal, you're going to say we're going to talk about our waves being close together. You're going to write gamma ray. I think you have 1, 2, 3, 4, 5, 6, 7, 8, 9 blanks. Is that correct? Yeah. So you're going to have gamma ray. Those are the most damaging. Gamma rays will kill you. Fortunately, a lot of the gamma rays, they're coming from space, they're coming from the sun. A lot of those are deflected by our atmosphere, and so we are, not hurt. The next one you're going to do is X-ray. If you've ever had an X-ray taken, you don't want to have like an X-ray taken every day, right? When I used to be the X-ray technician at the vet clinic where I worked, and I had to wear a big lead apron. all the time to protect my body from getting exposed to X-rays. Then comes UV light, ultraviolet. It's on the other side of violet. It can also damage you, that's sunburn. Then we have visible light, right here. That's what we see. That's Roy G. Biv. Then past the red, we have something called infrared. Infrared, you could say, is heat light, if you will. You see the special glasses and whatever. Microwave, which we, cook food in. That's the microwave oven is using those kind of waves. We have TV, and then we have radar, and then the last one we have on there is radio. And it's showing you how big these waves are. So a gamma ray is as big as an atomic nucleus, so small. X-ray is a little bigger, the size of an actual atom. The ultraviolet is the size of molecules. Visible light's the size of microscopic creatures. What's this? A needle point is infrared. Butterflies. What do you mean butterflies? That doesn't make any sense. Oh yeah, they're getting bigger. They're getting bigger. So why is it? That's bigger than this. Okay, butterfly, then humans, then radio waves are the size of buildings. So they're huge. They're huge, and they're coming in these windows right now. They're bombarding us. I think I have a little video for you. When the wavelength is large, the frequency is small. When the wavelength is large, the frequency is small. When the wavelength is small, the frequency is large. So as a light wave's frequency increases, its energy increases. Frequency increases, energy increases. As its frequency decreases, its energy decreases. As a light wave's wavelength increases, its energy decreases. So its wavelength increases, its energy decreases. As its wavelength decreases, its energy increases. So light with a shorter wavelength than visible light have higher frequencies and higher energy, therefore they're dangerous, including gamma rays and UV rays. And I think that's easier to see when you see those little visual, at those waves that are all compact like that are coming at you like a bullet. All right, good? All right, let's watch this.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Twice for some reason. Okay, so gamma, UV, X-rays are all blasting us from the sun. Unfortunately, and fortunately, not unfortunately, the atmosphere is protecting us. So there's the Earth. We have this magnetic shield in our atmosphere, which is actually deflecting a lot of that. So yeah, somehow that got designed that way. How lucky for us, right? All right, so now that we understand light, we're going to take that and apply it to what was going on with all those things that they were using in the tube, those gases in the tube. We're going to be looking a little bit at what is known as quantum theory by a guy named Max Planck. Max Planck. All right, and so Planck came up with the idea that light is probably traveling in these packets rather than waves. Up until this time, they were all pretty convinced it was waves. Now they're thinking this is more consistent with packets, but then other times it's more consistent with waves while we have the dual theory right there. So the frequency, and now we want to know the energy relationship with light right here. And we're going to use what's known as Planck's constant. This is Planck's constant. All right, so the quantum energy of a photon. So we are going to write that part right there as an F. So E equals HF. Do you have that written down in there already? E equals HF. That is Planck's constant. All right. Well, actually, H is Planck's constant right here. And H equals 6.626 times 10 to the negative 34 joules per second. All right. So we're going to use that. So we're going to use these different formulas, or the proper word would be formulae. That is the plural in the Latin. Of light and energy. So we already know this formula right here, finding our frequency. We can move it around to do that. We know that the speed of light is 3.0 times 10 to the 8 meters per second. And then we're going to see how's the energy associated with that. So we're going to take our frequency that we will be able to compute over here and put it in to find our energy by taking our frequency and multiplying it by Planck's constant, which is that number right there, 6.63 times 10 to the negative 34 joule hertz. So joule is the energy thing, and remember we already looked at hertz, which is our frequency thing. So a wavelength is in nanometers. We have 10 to the negative 9. That's our nanometers meters conversion relationship. Our frequency is 1 over seconds equals hertz, and our energy is in joules, named after Mr. Joule, who was working with energy. And we're using that because Planck figured that out. So let's just trust Planck on that one. So we're going to do an example now. A light wave has a frequency, we've got the F right there, of 2.3 times 10 to the 16 hertz. What is its energy? So do we have that? I should have had that little formula right in there. So we know this is Planck's constant right here. This is C. All right, so what's the next thing we're going to do if we're trying to find the energy? All right, we're going to use this, right? So we have our H all the time. We have our F right there. And we're going to do that math and end up here. 6.63 times 10 to the negative 34 times 2.3 times 10 to the 16 hertz, and we're going to end up with only joules. And joule is the unit for energy. Okay, so joule is energy. Planck's has both of them in there, right? So we're going to come out here. So we're going to end up with our energy is going to be 1.5 times 10 to the negative 17 joules. You'll have a couple of problems like that in your, and this is really physics right here. So if you end up taking physics someday, you're going to become very, very good friends with Max Planck and use his constant all the time. All right, now's where we go over to 3B. And we're going to take all of this information we know about the way light acts and how we are sending it through and everything to find out the design of atoms, and this gets really crazy. All right, it brings us to Niels Bohr. So Niels Bohr was fascinated with that experiment of the light when it shone through, that every element had its own color. And he said, that is so cool. Why is that happening? And so he developed a science called spectroscopy, and it led to a new model. It's going to be very similar to the planetary model. We're going to call this the Bohr model. There's going to be a little refinement of it, and then Bohr isn't exactly right all the way as far as we can tell, which is going to bring us to the model we're using right now, which we use Bohr's model of the atom all the time because it is so easy. All right, it's so easy to visualize. So the idea is, of course, we have everything in the middle. That was all correct. Okay, so Rutherford was right on that. But what Bohr decided was that what was the light? Where was the light coming from? When we shine the electricity through it, why was it glowing? And he decided what was going on is the electrons were actually jumping up and down. They were jumping out of their orbit. The energy was sending them somewhere, but then when they came back, the energy was released, and it was released in the form of light. All right, so we think that it looks like this. Now, he's not exactly right. Atoms look something more like this. Yikes. This is called the quantum mechanical model, and we'll get more into that here in just a second. All right, so the idea is that instead of, let me go back to Bohr. Okay, we have the nucleus, and we have electrons spinning around like our moon spins around, rotates around the Earth, right? Like that. And so, but when they did a few tests, they started seeing that there was something weird about the electrons. What Bohr did to change Rutherford's model was to say, let's say this electron right here can be anywhere in here. So we think it's a cloud. It's not spinning in a fixed orbit like the moon is in a fixed orbit. It's spinning in a cloud. And that cloud can be here, it can be here, it can be here, it can be here, it can be here, you know, all the way here, but not beyond here. So it'll stay up in this energy level. This is an energy level. This is a lower energy level. The closer it is to the nucleus, the lower the energy level it is. All right, and so doing experiments on that, they started to see, well, that they're not acting like they're going in a circle around it. So I might get a picture of the middle, and then the electrons spinning around, but they're like in a cloud covering it. They could be anywhere within their energy. What we call it a shell, which is a little bit unfortunate. We call it a shell because it seems solid. It's really empty space with these things spinning around, and they're spinning around in something besides spheres. All right, so some of them are spheres, but some of them are this shape. Okay, so this is called the s orbital. S orbital means that it's spherical. These, however, are called the p orbitals for dumbbell shaped. I don't know what the p stands for, but they call them dumbbell shaped, like you're lifting up a dumbbell. And these are really bizarre ones. Check this out. Okay, we really don't know this, y'all. We have some x-rays that kind of show some interesting things like this, but these are the d orbitals. Okay, so we have s orbitals, s, p, d, f orbitals. All right, do I put f in? Oh yeah, look at f, yikes. Okay, this is chemistry too, by the way. We're not gonna deal with d and f orbitals. We're only gonna deal with s and p orbitals. All right, and so the deal I want you to know about them is for every orbital, spherical, or p, there only 2 electrons can go in there. So 2 electrons in here, 2, 2, and 2. So we put all these three together. I'll show you that in a second. So that I have 2 in the spherical, I have 2, 4, 6 in the p orbital. Do you see why I have 6? Because there's 2 in each one of those things, in each plane, x, y, and z. And these have 2, so 2, 4, 6, 8, 10. So 2, 4, 6, 8, 10. And then 2, 4, 6, 8, 10, 12, 14 for the f orbitals. Remember, we don't have to worry about these. I'm just giving you that information. All right, so how did we get here? Way back in the day, the Hindu philosophers said we have elements called fire, air, water, and earth. Then Democritus comes along and he says, you know what? When you get closer to that beach, I see those little grains of sand right there. I'm going to call those indivisible things atoms, and depending on what they are, they're shaped differently. So water atoms might be shaped like this, iron like this. Lord Kelvin comes along, he says, oh, I think it's more something like they're shaped like a pretzel, a twisted knot kind of a thing. That got replaced with J.J. Thomson's plum pudding, which got replaced with, well, we know that Rutherford's in there with the planetary model that left him out of this one. Bohr is kind of a modification of the Rutherford atom. And then comes the quantum mechanic theory is where we are now, with our orbitals being different shapes. So the quantum mechanical model shows electrons get excited and jump to a higher orbital from the lower to the higher by adding heat or other energy. They absorb that, they get excited, that's called the quantum leap. But they always go back down to their original energy level. They always drop back down. And when they do that, they emit light. That's called the quantum fall. Okay, so that's where the light is coming from, is it falls back down and it glows. And it glows in a specific color based on whatever element we're talking about. Remember those salts that I burned the first lab we had? Yeah, they were different colors, right? That's because they were putting off a different spectra. So we'll test that next week. All right, so here we go. It got bumped up here because energy was put into it. Now it's dropping back down and leaving this out right here. You can see it again, dropping back down and then releasing that light. It's coming down to the level here and energy coming down. It's called the quantum leap, the quantum fall, and then watch this. So it's up in the top, it's going to fall down, and now it's going to go back up, and then it's going to fall down. Energy in, energy out. Get it? And when the energy's out, light is there. But energy had to come from somewhere. We had to put the energy in to begin with. Okay. All right, so here's our p orbitals. We have one going on the x, one going on the y, and one going on the z, if I said that right. Yes. Oh, I didn't. Px, py, pz, and then the whole thing put together. I've tried to make this model before, like with balloons, you know, and it gets kind of difficult to do. And remember, two electrons, 2 electrons, 2 electrons, 2, 4, 6. That's really the important thing you need to know. All right? So let's watch. This doesn't have any sound or anything, but it shows a really cool way that they put this together. So it gives us a little three-dimensional visualization. So first comes in our 1s orbital. This is 1s, and it's a sphere. Then the next energy level up will be our 2s orbital. So it'll come in another sphere bigger to go around it, you know. So we have two electrons now, 2 more electrons. And then we're going to come in with our 2p. That's the energy level. 2 is the energy level. Here comes the first one. That'd be x. And then it's going to come y, which I thought that one coming out would have been z, but. And then now it's going to come in z. So there's 2, 4, 6. And the s's each had 2. 7, 8, 9, 10. We're looking at neon here. There's kind of our three-dimensional, kind of cool looking, huh? Now we're going to bring in another s that comes around here that covers the whole thing up with our 3s, okay? All right, so the quantum mechanical view of neon, we're looking here. Are you supposed to draw this? So neon is number 10 on your atomic, on your periodic chart of the elements, so we know it has 10 protons. So it has 2 electrons in the first s orbital, and then we're going to look at these 1, 2, 3, 4, 5, 6, 7, 8. 6 of them in the p, 2 of them in the second s orbital. Those are energy levels, okay? So there are 2 in 1s, 2 in 2s, 6 in 2p. And this is going to become really important here in a second, okay? It's actually kind of fun. All right, so how do we build them up? All forms of matter try to stay in their lowest possible energy state. Remember I said they always want to drop back down. If you put electricity and they have a quantum leap, they're always going to fall back down, the quantum fall. That's because they always want to go home. Electrons always want to go home. There's no place like home. Furthermore, they're lazy. I can relate. They're lazy, okay? So they go back home. The ground state is that lowest possible energy state. In other words, they're not being excited by electricity or any energy being added to them. By following electrons through their energy levels, we can begin to picture them and understand something known as an electron configuration. If you're going to have a difficult time in this module, it might be with the electron configurations, but you shouldn't, because it's actually a lot of fun. And it's super helpful, all right? So I've come to make peace with electron configurations, more so than with Lewis dot structures. So we'll talk about those another time. All right, this is what an electron configuration looks like, okay? The electrons are distributed into energy levels. We have our 1s, we have our 2s, we have our 2p. The 2 and the 1 refers to the energy level. So in this particular configuration, the lowest energy level is 1, the highest energy level is 2. That's the highest energy level we get, okay? So we have these little numbers up here. This is so much fun right here. We're going to count them. We have 6, 7, 8, 9, 10. I have 10 electrons right there. So I can tell you this is the electron configuration for neon, because it has 10 electrons, okay? And remember, we also know that we define it by the 10 protons that it has, but we're talking chemistry now. And chemistry is about how the electrons get moved around and traded and shared and that kind of thing, okay? So those are counting the electrons right there. Every element has its own electron configuration. So when you're looking at your periodic chart of the elements, you're going to see the reason we're going to finally, the mystery is going to be solved as to why it's arranged the way it is. All right, so we have two groups over here, okay? These two columns going down are our s orbitals. That's the energy level over there, s. These are our p orbitals. And these crazy guys in the middle are our d orbitals. Okay? So something you need to know, okay, because you will be following through the d. D has 10. We don't need to worry about what the orbitals look like, because they have those weird, crazy donut-looking things. But there's 10 electrons in there. I just need you to know that. There's 6 electrons here. 1, 2, 3, 4, 5, 6. There's only 2 in this energy state. Am I making sense to y'all? Okay, so there's 2 electrons in the s energy state. There's 6, because of the way they're shaped, 2, 2, and 2, okay, in the p, and then there's 10 in the d. Now notice you're not seeing any f here. Notice there's that, in your chart, there's that whole group that are pulled down below everything. Okay, those are the f's, all right, and we will not be messing with those guys, all right, we're going to leave those guys alone. They've been pulled out. If you look at their numbers, they've been kind of pulled out of the middle there because they act funny. F for funny. Freaky. Okay? And we're not going to mess with them. All right, so, but in order to find the electron configuration, we're going to be following through here. So the first thing we need to know is we're going to put helium, notice what color it is, helium in a special spot. We're going to pull it right over here next to hydrogen, okay? So it's going to be in the s orbital block. So it's not p, it's s, because it's so small, okay? All right, ground state is the lowest possible energy. So here we're going to see 1s, 1, that's hydrogen. 1s, 2. How many electrons does it have? 2. All right? And so we're going to follow those down right here. When you get down to over here, you're going to have to add them up. So you can't say each one of these has 6. No. Each one of those has something we're going to add all together right here. All right. We call the first 2 columns the s orbital block because the last electron of the atom is found in a spherical orbital. Okay? Since each orbital can only have 2, the s orbital block is only 2 columns wide. How about that? Okay? The next group represents those in the d orbitals. They have 5, each having 2. That's 10. That's why that group in the middle, there are 10 in there, because d goes with 10. And then our next one, the p, there are 6, so there's 6 in there, over there in that group. So that's why it's arranged the way it is. Pretty cool. And the fact that it actually works. I mean, it works. Everything they tried to work with this thing, all of a sudden everything was fitting in like a beautiful puzzle. How about that? All right, the rows represent the energy levels. Higher the energy, the farther you go down. Okay, so we're going to try to write the electron configuration for these 3 things. Now we're going to watch the guy do it with the video, and I need you to not fall asleep. I need you to watch very closely. He goes into very much detail on this, but you're going to see, I'll follow along, so don't go to sleep.
In the next 3 examples, we're going to be determining some electron configurations. Now remember, the periodic chart is laid out so that you can determine the electron configuration by just looking at the chart. The first 2 columns on the chart, 1A and 2A, are for those elements whose last 1 or 2 electrons are in an s orbital. The last 6 columns, 3A through 8A, are for those elements whose last few electrons are in a p orbital. And the middle block, 1B through 10B, are for those elements whose last few electrons are in d orbitals. The rows in the periodic chart represent the energy level of the last few electrons. Row 1 is energy level 1, row 2 is energy level 2, and so forth. That's true for the s orbitals and the p orbitals. For any electrons in d orbitals, the energy level is determined by taking 1 from the row number.
I forgot to tell you on that.
So for example, if you look at that first row of d orbitals, that's in row 4 of the periodic chart, but that represents energy level 3. Alright, with that information, we can determine the electron configuration of any element on the chart. The first problem in this example asks you to determine the electron configuration of carbon. The way we do this is we simply step through the periodic chart until we arrive at carbon, keeping track of the electrons as we go. The very first square on the periodic chart is hydrogen. It's in row 1, so that means energy level 1, so we put a 1 there. It's in the s orbital block, so its electron is in an s orbital, so we put a little s there. And there's only 1 electron, so we put a 1 as a superscript. That means 1 electron. So the electron configuration of hydrogen is 1s1, and that means it has 1 electron in the 1s orbital. Well, we haven't reached carbon yet, so let's just keep going. The next box is helium. Now remember, helium's usually in group 8A. For purposes of electron configurations, though, we artificially pull it into group 2A. Helium's in the s orbital block, so the electrons that belong to helium are in the s orbital. There are 2 of them, and it's on row 1. So its electron configuration is 1s2, indicating that it has 2 electrons in a 1s orbital. Alright, let's keep going. The next stop is lithium. Lithium's also in the s orbital block, so its last electron is in an s orbital, but it's not in a 1s orbital. Lithium's in row 2, so its last electron is in a 2s orbital, so we put 2s1. So lithium's electron configuration is 1s2, its first 2 electrons are in a 1s orbital, 2s1. Its last electron is in a 2s orbital. So do you see how this works? Every time I step to another box in the periodic table, I'm adding 1 more electron. I determine where to add it by the column and the row that the box is in. So let's keep going. The next stop is beryllium. It's in the s orbital block, so its last electron is in an s orbital, and it's in a 2s orbital. So we've got another electron in a 2s orbital, so that means 2s2. The first 2s electron came from lithium, the next one came from beryllium. Let's keep going. Boron. Boron's in the p orbital block, so its last electron is in a p orbital. It's still in row 2, so the energy level is 2, so it has its last electron in a 2p orbital, so we put 2p1 to indicate 1 electron in a 2p orbital. Finally, we reach carbon. Carbon's also in the p orbital block, so its last electron is in a p orbital. It's still in row 2, so we put 2p2 to indicate we have 2 electrons in a 2p orbital. So that's the final electron configuration of carbon. 1s2, 2s2, 2p2. Now please understand, these electron configurations are very important. Obviously they're important, or the entire periodic chart wouldn't have been laid out to make it possible for you to figure them out. As you'll learn in Module 7, the electron configuration tells you a lot about the chemistry of the atom. Now that's not the only thing it tells you, it also actually tells you where every electron is in the atom. So these electron configurations actually describe the atom. In this electron configuration, for example, this tells us that carbon has a total of 6 electrons. The first 2 are in a spherical orbit, close to the nucleus. 1 means first energy level, that's close to the nucleus. S means spherical orbit, and 2 means there are 2 electrons there. Then there are 2 electrons in a bigger spherical orbit. 2 means it's farther away from the nucleus, so it's bigger. S means it's spherical. 2 electrons means there's 2 electrons there. And then finally there are 2 more electrons in dumbbell-shaped orbits that are about as far from the nucleus as the second spherical orbit. So these electron configurations look a little arcane, but they're very, very meaningful. All right then, let's work on the next electron configuration. The next electron configuration is that of chlorine. Now think about it for a minute. We don't have to start over here. After all, we determine electron configurations by walking through the chart, box by box. Well, in order to get to chlorine, we've got to pass through carbon. So there's no sense of erasing everything and starting over. Let's just continue on from carbon until we reach chlorine. The next box is that of nitrogen. We add another electron, but it's still a 2p electron because nitrogen is still in row 2 and in the p orbital block. Then the next box is oxygen. We add another electron, but once again, it's a 2p electron because oxygen is still in the row 2, the p orbital block. Then we move on to fluorine. Still in the p orbital block, still in row 2, so that's just another 2p electron. And then we hit neon. Neon's also in row 2, p orbital section, so that adds another 2p electron. We're now up to 2p6. There are 6 electrons in the 2p orbital all the way up to neon. Now we go to the next box, which is sodium. Sodium's on the next row, 3. So its energy level is 3. It's back in the s orbital block, so the electron we're adding here is an s orbital electron. Then we go to magnesium. Magnesium's still in row 3, s orbital block, so the new electron just goes in 3s again, and we have 3s2. The next box belongs to aluminum. It's still in the 3rd row, but it's in the p orbital block, so the next electron we add goes in the 3p orbital. All right, then we continue. We go on to silicon next. It's still in the 3p section, so we just add another 3p electron. And we continue that way. The next box is phosphorus. We add another 3p electron. The next box is sulfur. We add another 3p electron. And then finally we come to chlorine. Chlorine is the 5th box in the 3p row, so its electron configuration ends with 3p5. So this is the electron configuration of chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. Just to make sure you really understand this, we're going to do one more element, silver. Silver's in row 5, column 9b. All right, we have to walk through the chart until we reach silver. Well, there's no sense starting over. After all, if we're going to walk through the chart, we'll reach chlorine before we reach silver. So we might as well take what we've done so far and just add to it. All right, well, the next box along the way to silver is argon. Argon's still in row 3, the p orbital block, so we just add another p electron, and we have 3p6. All right, now we're going to speed up. We want to do this a little more quickly because we have to get all the way down to silver. The next 2 boxes we encounter are in row 4, the s orbital block. That gives us 2 electrons in 4s. So we'll just write that down, 4s2. Then we encounter the d orbital block. Now remember, to get the energy level of the d orbital elements, we have to subtract 1 from the row number. So we're in row 4, but the energy level is 3. They're d orbitals, so we have 3d. We have to go all the way through this block. There are a total of 10 elements there, so that'll give us 10 electrons to throw in the 3d orbitals. So let's just write that, 3d10. All right, we've got to go to the end of the row still. The next set of elements are in row 4, but the p orbital block. So we have to write 4p, and there are 6 of them, so I get 6 electrons in 4p. Now the next 2 elements are in the s orbital block, row 5. So I've got to have 5s2 because there are 2 elements there. Now I'm finally at least in the row and the block that we find silver in. So I've got to walk all the way over to silver. I'm now in row 5, but remember in the d orbital block that's energy level 4. So I'm filling 4 d orbitals at this point. In order to get to silver, I've got to walk through 9 boxes. So that's 9 more electrons, so they all go in 4d, and the final section is 4d9. So that's the electron configuration of silver. It's a lot longer, but it's just as important as the other electron configurations we just determined.
Okay, so you get it? And if I went through and added up each one of those numbers right there, I would come up with the number for silver, whatever that number is. Okay, so that's how many electrons would be in there. Okay, so I apologize, I forgot to mention to that energy level drop right there in the D's. We go down to the energy level below it, just to call it that way. Also, I wanted to mention to you that, like, say for instance in the p orbital, let's say in carbon, so carbon had 2p2, right? So 2 electrons there. And remember, they're like this, the dumbbell. They can be in this part of the dumbbell, or this part of the dumbbell, or this part of the dumbbell at any given time. We're never exactly sure where the electrons are in their orbital. That's called the Heisenberg uncertainty principle. Okay, we're not really sure where they are ever. And so, like with the D, they could be in that donut one, or that round one, or that side one. They could be anywhere. But they're somewhere in there. All right, but now I will give you, look here, we have a shortcut for electron configurations. Awesome. We can do that by doing what we call the abbreviated electron configuration. So here's how we do. We find the symbol. So for this one, we're going to be trying to do zinc. Let me tell you, my chart that I have for college had all of those little electron configurations written in the box. They were already written, and I just have to look at them. I was like, oh, there they are. Yes, that's cool. And I actually got one for my students one year, and I noticed they had them in there, and I had to take them away because. So I had to get you these simpler ones. You have to do it yourself. Although the students never saw them. The students didn't notice them. Yeah, so, and I didn't tell them. So here you go. We're going to go here to zinc. So the first thing, we'll find the symbol. So the symbol is Zn for zinc. And then the next thing we're going to do is we're going to write the noble gas that came before it. So the noble gas that comes before zinc is all the way back here to argon. We take argon and we put it in brackets. And then from there, we just add, so we have our argon in brackets, then we say 4s2, 3d10. So I don't have to write everything that came before it. This is an abbreviated version. So for instance, if I were trying to do silver again, I would put krypton in brackets and then just do my 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it'd be much shorter, right? So if I ask you to do an abbreviated one, let's do one right now. Abbreviated configurations for SR. Let's find SR. SR. What is SR? Sure. There it is, right there, number 38. Okay, so what is the noble gas before it? Looky, looky. Krypton. I'm going to take it, put it in brackets. It's going to be an easy one, isn't it? Because it's over here in the S's. What's it going to look like? Oh, before we do that, let's find SE real quick, too. SE's all the way over here. Okay. It's going to look like krypton and 5s2. See? See how I got that? Yeah? Those are much fun, more fun, right? Okay.
What if you do one of the ones that's in the brackets?
What about
Like
it?
if you do a gas instead.
Like if it asks you that?
Yeah.
Well, then you have to do the whole, you can't do a,
Okay.
unless, what is the abbreviated electron configuration for argon? Or else you would do neon and add all the other stuff to it.
Okay.
Like I'd go back to neon, and then I'd add 3s2, 4p6.
Okay.
3p6, sorry. Okay, now we're going to go to selenium right here. So we're going to have argon. That's K on that one. Argon 4s2, 3d10, 4p4. Okay, so much shorter instead of doing all that stuff all the way to argon. All right, so tell me what this element is. I think you're right. Yeah, how'd you get it? How'd you do it?
The number.
Add all those little numbers up. We added up to 26, right? We can go see what number 26 is on the chart. Yeah? Okay, good. Let's see. Columns 1 and 2 are called the s orbitals. Columns 3 through 8 are called the p orbitals. I don't know if you had those blanks in there. I think this was, and D and F blocks, orbitals fall in the center. Okay. So how do you do it? You determine the energy level and the orbital of the element. You go through the chart until you reach the element. If it's in the D block, go down one energy level. I probably should have had that prior to that. One thing I wanted to mention to you, that we have this remarkable miracle going on here, and that is the neutron and proton are essentially the same mass. Okay, so they're about the same mass. But the proton, it takes 1,830 electrons to equal the mass of one proton. But one electron has the same negative charge as a one positive proton. In other words, the charges balance out, but the masses aren't even close.
That's crazy.
That's nuts. And that's a miracle that that's going on like that, okay? So we have those balanced out that way. The electrons are so tiny that their mass is negligible. We never even think about them. Even we have a really large atom, we never even think about the weight, the mass of the electrons in the mass of the overall, because it's so negligible, they're so tiny. Using light in chemistry, we're going to use a little bit of this next time. You know, this is one of the more fun labs, in fact, where we use light spectroscopy. And so I'm not going to have a fancy thing like this, although I used it was actually fancier than this when I was at UT. And I guess it was chemistry class. I almost feel like it was physics class, but I remember being in the chemistry building. And we'd put a little element in something and we'd start to make it glow. And then we'd shine it through there and look at it, and it would come up and we'd see the little color on a little screen. And then it would be an unknown, and then we'd have to say, okay, well, it was this wavelength, this wavelength, this wavelength. Those together, I look at the chart, the gas that I'm burning over there is whatever gas. So it's pretty cool. So for instance, if you put mercury in there, the spectral analysis is going to look something like that. Wow, it's got a lot of lines on it. Whereas neon only has these few lines. When we look at neon, we get a purplish color. Cadmium, these, iron, this. So it's a fingerprint of each particular gas. And we're going to be doing those same salts next time, looking at them through a little cheap-looking spectrometer, and try to get that done. Okay. And I think, we don't have the electric pickle, sorry. I think we're done. Oh, I was really worried about getting through this lecture on time now, so we did, we got through on time. Yeah. All right, and I can now stop the recording.